All right, welcome back. Here we are again, working with inferential statistics involving the proportion. So, in the previous lecture and video, we talked about the confidence interval for the proportion. So, given the confidence interval, we can say, hey, we're 90% certain that the proportion is contained within this interval. So, pretty much anything inside our interval we believe, anything outside we don't believe. Right, so these confidence intervals, they're purely data driven. Okay, but other types of inferential techniques, usually we're testing a claim. Right, someone makes a claim about the real world and we want to test their claim. Okay, so the big difference between hypothesis testing and confidence intervals, they're both methods in making decisions using data, but with hypothesis testing, it's really driven by a claim, right? Some kind of hypothesis made about the real world. And intervals, they're purely data driven. Okay, so as a general outline here, okay, so as far as hypothesis testing, it follows the formal scientific method. Okay, it's nothing new that's unique to statistics. It's something that we see in every field of science, and one that Albert Einstein, we can believe, used in his methods. But here for hypothesis testing, we're just saying it's a procedure that enables us to choose between two claims. Okay, so when we have variability in our assignments. Okay, so pretty much at the end of this procedure, we decide one of two things, right? And so, but our decision, it's not 100% certain because there's variability, right? So for example, the sample proportion, right? For every sample I collect and observe the sample proportion, right, I don't know what number it's going to be. It's random, right? It's kind of a random outcome, right? But in practice, we have to make a decision based off that sample proportion. And so that's what we're going to learn today, right? So as far as the formal procedure goes, we more or less follow a four-step method. One is state a hypothesis, a claim about the world. The claim will be weighted against a neutral skeptical claim. So pretty much this is like maybe our research hypothesis, right? And then this other claim is pretty much the opposite of that, maybe a skeptical claim or something that's neutral. In step two, what we'll do is we're going to determine how we will use data to make decisions, and make sure to have enough data to avoid mistakes. Okay, and then three is we're going to collect data and compare them to your expectations. And four, state your conclusion. Okay, so we've kind of done these things. We've done these things informally, especially in these examples here. We were talking about helper versus hinderer, right? Our claim is that these babies are more likely to observe helpful behavior and in fact favor it over hinderer behavior. So, but really, when we were simulating outcomes of this experiment, we were assuming that there was no preference, right? 50-50 chance. Right, so that's kind of like, our hypothesis was that they're more likely to favor the toy, the helper toy, right? And then the neutral skeptical claim is, well, let's see how likely is it that we observe this, given that there's no preference, right? 50-50 chance, right? And so, and then we looked at data, right? We looked at data. 14 out of the 16 babies selected the helper toy, and we compared that to the outcomes we would expect to see if it's 50-50 chance. Right, so if it's 50-50 chance, we would expect 8 out of 16 babies select the helper toy, but of course, we took into account the random distribution of the proportion, so we actually had a picture there. Okay, we did the same with all of these as well. Okay, kissing the right way, right, we assume 50-50, rock, paper, scissors, we assume a third chance, Halloween treats, we assume 50-50. Okay, so let's get into it here. So what we're going to do here is just kind of give examples of each of these individually, and then in the next section we'll put them all together to perform a hypothesis test. But as far as the main ingredient is, we need our hypotheses in order to first begin with our test, right? So here it says the alternative hypotheses, denoted HA, is the research hypothesis, right? It is usually a statement about the value of a parameter that we intend to demonstrate is true. So if you remember, when we were doing the trick or treat example, right? We assume that perhaps there is an obesity. There is an obesity epidemic going on in kids aged 3 to 14 years of age. So then we would assume that when they're presented with the candy or the toy, that the proportion or the probability of selecting candy, that was going to be greater than 50%, right? A majority of them are going to pick candy over the toy, right? So this is like the research hypothesis. This comes from the study, and this comes from the obesity epidemic that we want to test. So our null hypothesis, though, which is denoted H naught, okay, it's not H0, HO, it's just H naught, is the neutral or status quo skeptical statement about the population parameter. So it's kind of the opposite. So our statement here is saying that we suspect an increase, right? More likely to select candy, right? So our null hypothesis is going to assume that there's no obesity epidemic, right? There's no obesity epidemic in the kids 3 to 14 years of age. So in that case, when they go up and select the candy or the toy, it's 50-50 chance. Okay, so this is our null hypothesis. So usually how we write them is we write the null hypothesis first. So saying the null hypothesis is that the population or proportion of candy selected is 50%, versus the alternative hypothesis that the population proportion of candy selected is greater than 50%. So usually that's how we set it up, the null and alternative hypotheses. And the setup is very crucial because we're going to use this value when we calculate what we call our test statistic, and we're going to use whatever sign is here is going to determine how we're going to find our p-value. So, here's just another example in constructing the hypotheses. So the name of the game here is going from this short passage to this statistical language here, and vice versa. So here it says, historically, about 70% of all U.S. adults were married. A sociologist who believes that marriage rates in the U.S. have declined will take a random sample of U.S. adults and record whether or not they are married. Okay, so the alternative hypothesis or the research hypothesis is going to be, they're assuming the marriage rates have declined, right, in the U.S. Right, so that declined is just saying, well, in comparison to 70%, if it's declined, we're saying that this P, which is the proportion of U.S. that is married, is going to be less than 70% or 0.70. So whenever we're given proportions, they could be in percentages, but as far as when we do the hypothesis test and the math, always convert to decimal. Okay, now the null hypothesis, remember, is the neutral status quo skeptical statement. So in here we're just going to assume no change, right? There's no change in marriage rates in the U.S. So that's kind of a neutral approach, right? We're just saying that P, the proportion of U.S. adults that are married, hasn't changed at all, and it's still 70%. So finally, we have our null hypothesis, which is saying the population proportion of married U.S. adults is 70%, versus the alternative hypothesis, which says the population proportion of U.S. adults that are married is less than 70%. Okay, so sometimes that could be 80% of the game, is just to be able to establish the correct null and alternative hypotheses, and then the rest is more or less procedural. Okay. All right. So just in general, as far as the type of null and alternative hypotheses that we'll see for the proportion, in general, there are one-sided and two-sided alternative hypotheses. Okay, so we're looking at the alternative. One-sided indicates an increase or decrease in population parameter value in null hypothesis. Two-sided indicates that the population differs from the value in the null hypothesis. So, for example, this is what two-sided look like. Okay, null hypothesis is saying it's equal to some amount, where the two-sided is just saying it's just not equal to some amount. So in the study, we don't know whether there's an increase or decrease. We don't know whether it's declined or not. So in this case, we put two-sided. That just means not equal to. All right. So in this case, we could reject it. Well, we'll get to rejection soon. Okay, but here, as far as one-sided, there's one-sided left and one-sided right. So here it's just saying the alternative is saying that the population proportion has decreased from some amount. The population proportion has increased from some amount. Okay, so in here, as far as the types of alternatives we'll see, these are the only three kinds that we'll see. Okay, so in here for less than, we have to look for those key words like declined or decreased or less than, something like that. For this alternative, we have to look for the key words like increased, and greater than, and words like that. And then for these kind of two-sided alternative, it's kind of the direction's not very clear. Sometimes they want to test whether or not it's equal to P naught. So that would be indication of a two-sided test. Okay. So as far as our testing goes, so we set up the null and we set up the alternative. One thing that's important to know in hypothesis testing is that we assume whatever value in the null hypothesis, we assume that to be true throughout the entire test. Right? So we say the null hypothesis always gets the benefit of the doubt and is assumed to be true throughout the hypothesis testing procedure. Okay. So if we decide at the last step that the observed outcome is extremely unusual under this assumption, then and only then do we reject the null hypothesis. So if you look back at the trick or treat example, right, I simulated the sampling distribution of the sample proportion, assuming that there's no preference, right, 50-50 chance. So what this distribution is, that's the distribution of all the sample proportions, assuming no preference. And so what you can see here is, proportions between these two numbers here are going to be what we can expect to see if the true proportion is this, right? So what I'm saying is that we can expect to see these sample proportions around here, given that the population proportion is 0.50. But also it's kind of indicating here, like around here, these are very extremely unusual sample proportions to see. So what this statement is saying here is that if we get a sample proportion that is out here, it's very extremely unusual to view that, given that the center is 50%. And in that case, we would reject the null hypothesis. All right, so just to kind of illustrate that, right, that's what's going on here. All right, so we assume the null hypothesis to be true. So what does that mean? It means we're assuming that the sample proportion is going to be centered around the null hypothesis proportion, 50%, right? And so from there, we can find the standard error of the sampling distribution, right? We can make this graph here. So what happens is that if we get something extremely unusual out here in the tails, because remember here our alternative is greater than, so we suspect the proportion is larger than 50%. So that's why extremely unusual are very large values here. Okay, so here we're going to reject the sample proportion is out here. Okay, so something very weird or unusual occurs, there's a surprise, then we're going to reject the null hypothesis. Okay, and that's a kind of funny concept to be presented in statistics. Hypothesis testing is a very funny kind of concept. But it's kind of like when you're in the courtroom, or not you in the courtroom, but when the defendant's in the courtroom, right, they're innocent until proven guilty. So throughout the entire trial, the defendant is presumed innocent, right? We assume that they're innocent until proven guilty. So then what we say is, well, how likely is it that your fingerprints were at the scene of the crime, and we have video of you at the scene of the crime? How likely is it that we observe it, given that you're innocent? And it's not very likely. So it's kind of like something out here. If you're innocent, then we have some actions. We know what you're going to be doing. But if you're guilty, something weird is going to add up. Okay, so we'll get more on that as far as with more examples later. But really, this kind of funny thing with hypothesis testing, we assume the null to be true, and then we make a decision. Okay, so once we have established our null and alternative hypotheses, we need to state the significance level of our test. Okay, so just like confidence intervals, right? 90, 95, 99, those represent capture rates, right? And those tell you how likely is it that we have a good interval? Okay, but here it says it is a name for a special probability. It is the probability of making a mistake, of rejecting the null hypothesis, when in fact the null hypothesis is true, usually denoted by the symbol alpha. So as far as our testing goes, right, either we make a mistake, right? I mean, either as far as our test, right, our decision, either from our data we're going to reject the null hypothesis, or we do not reject the null hypothesis, right? That's what our test says. But in reality, and that's something that we don't know, either the null hypothesis is true or the null hypothesis is false. So think of it this way, right? A defendant walks in the room, and in reality, right? They are innocent, right? They are innocent. And so our jury, they see all the data, and they're like our test, and they decide, and they find the defendant not guilty. So that's good, because the jury's decision matched up with the reality, right? The defendant was in fact innocent, and the jury found it through the evidence that they were innocent. So that's good. Our decision matched up with the reality. Now, in this case here, we have the null is true, but we decide to reject the null hypothesis. So what this is saying is a defendant walks into the classroom and they are innocent. The courtroom, and they are innocent. Okay, they are innocent. Okay, but the jury, they see all the data, they see all the evidence, and they find the defendant guilty. Okay, so pretty much what happens here is that we have an innocent person that is being sent to jail, right? So our decision does not match the reality, right? So obviously we want to avoid this type of error, and really it's impossible to avoid it, because remember, as statisticians, we don't know everything 100% certainty. I mean, no one does, but we're making the most educated decisions that we can, and we're saying that, hey, we're not perfect, and that's what this alpha is doing here. So in our tests, we don't go into how we do this, but this alpha here, right, we set it to be small in the beginning. So usually what we do is we give an alpha, we say our significance level is maybe 1 or 5 or 10%, right? Ideally, we want this to be small, okay? What these other ones are saying is what this outcome here is saying, the null is false, and we reject the null hypothesis. So this is saying a defendant who is really guilty, okay, they walk into the courtroom, and then the jury sees all the evidence and find them guilty, right? So once again, the guilty verdict matches up with the reality that the person is in fact guilty, okay? And then this last error, which we don't really talk too much about, but this is just the null in reality the null is false, but our test does not reject the null hypothesis. So what this is saying is that someone walks in the courtroom and they're guilty, okay, they're guilty, right? Then our jury, they observe the data, and then the evidence, and then they say that the defendant is innocent or not guilty. So pretty much in this type of error, a guilty person goes free, whereas in this error, an innocent person goes to jail. So in terms of the errors, we say type 1 error is the worst of the two. So that's why we just want to set it to be small. Okay, we set it to be small. Okay, so for example here, in testing our and going back to the trick or treat example, we have the null hypothesis is that proportion of candy selected is 50%, versus the alternative that the portion of candy is greater than 50%. So right away, once we establish these non-alternative hypotheses, we have to state the significance level. So we agree that we're going to use a significance level of alpha is equal to 0.05. And so we'll talk more about how they're selected, okay? But right now we'll just say that right now, I mean, they're all going to be like 0.01, 0.05, 0.17. They're going to be small because we want this type 1 error to be small. But we'll talk about how we pick these later. Okay, but here, so what does that mean? What does that mean? It says this means there's a 5% chance that we conclude there is a larger preference for candy than toys, when in reality there is no preference at all between the treats and toys, right? So what it means is that we're rejecting this claim and concluding the alternative when in fact this is true, right? So saying that there's a 5% chance. And one thing that's important that in practice that we always pick this alpha, right, prior to crunching our data, okay? Because as we'll see later, people can cheat and switch their alpha around so that they get the desired result. Okay, but this is the mistake. Okay, but at the same time, we're just saying, hey, we're humans, we're not perfect, and we don't 100% know everything for sure. But here's the chances of us getting it wrong. Okay, so I mean, typical values for the significance level are 0.01, 0.02, 0.05, 0.10. And usually we say 1% significance level, 2% significance level, 5% significance level, 10% significance level, and so on. Okay, but whenever you report the results for a test, you always have to provide the significance level. Okay, because typically the smaller the number, the more evidence, right? The smaller the significance level, the more evidence required in order to reject the null. Okay, but so once we get into, we establish the null and alternative hypotheses, then we establish our significance level. Okay, and what we say is that when we conduct this test, we're going to assume the null hypothesis to be true. Okay, and so meaning that my sample proportion should be centered around the null hypothesis proportion. Okay, and so you have to think about sampling distributions for the proportion. So what we look at now is the test statistic. So what this does, it compares the real world, right? The real world, which is our sample proportion, with the null hypothesis world, which is P naught, okay, the proportion from the null hypothesis. And it compares our observed outcome with the outcomes the null hypothesis says we should see. Okay, so for example here, we're saying the null hypothesis, the population proportion is equal to the null hypothesis proportion. Okay, maybe this is like 0.5 as it was previously. Then the one proportion Z test statistic is defined as this. Okay, so this is how we use our data. So really it's a Z score that we use for normal distribution, right? But it has more meaning here. So here what we do is we compare our real world sample proportion with the null hypothesis world, the population proportion, according to the null hypothesis. So we say, is there a difference, right? What's the difference between these two, right? And then we say, okay, there is a difference, but is it significant or not? So what we do is we compare this difference to the standard difference that we should expect to see. So remember, standard error here is just the standard deviation of the sample proportion. So what this represents here, this is the average or typical difference we should expect to see between the sample proportion and the null hypothesis proportion. Okay, because that's the center. Okay, so really, if the null hypothesis is true, then the Z-test statistic will be relatively close to 0, meaning like maybe between 1 and -1, or -0.5 and -0.5 and 1.5. And definitely values greater than -3 or greater than 3 are far away. So remember, because this is a standard normal, right? This is like a standard normal. So what am I doing here? I'm just using that 68, 95, 99 rule to kind of justify what is far away, right? What is far away, right? So make sure you review that and you understand that, because it'll make hypothesis testing a lot more intuitive if we can always interpret this Z-score here. So in this example that we did for the pumpkin data for the trick-or-treaters, so remember, we assume under the null hypothesis, so my P naught here is 0.50, and what the real world data is 0.5230, right? So this test statistic, I called it a Z-score, but now it's a Z-test statistic. So I compare my real world to the null hypothesis world, and there's a difference of 0.023, right? 2.3% difference. And so what we want to know is this difference significant or not? So what we do is we compare this difference to the standard difference we should see between any sample proportion and the null hypothesis proportion. And we roughly get 0.77. So that is that is the real world data produce a sample proportion that is 0.77 standard deviations greater than the null hypothesis of reality of 0.50, right? So in terms of like 68, 95, 99 rule, it's not really that far, right? This value is relatively close to 0. So more than likely, we probably will not, this is not enough evidence. Though it is greater, though the sample proportion is greater than 50%, it's not significantly greater. Okay, so in this case, we probably wouldn't reject this claim here. We would fail to reject the null. Okay. So in the last couple slides here, we just talk about the p-value, the surprise. Okay, so with this test statistic, pretty much we find the probability. So the p-value is a number that measures our surprise by reporting the probability. When the null hypothesis is true. Okay? When the null hypothesis is true. So, so a test statistic will have a value as extreme or more extreme than the value we actually observe. So p-value has a very, very funny definition. Okay, very funny definition. It takes a couple times to read through. But really what it's saying is, let's assume the null hypothesis is true. Let's assume that it's 50%. I go out and collect my data. How likely is it that I observe my data given that the null hypothesis is true, right? And really what they say is that, well, how likely is it that I observe my data and more extreme values? Okay, and so and if it's very unlikely, we reject the null. If not, otherwise we keep the null. So here, if p-values close to 0 mean we receive a surprise. Okay, meaning something, if the probability is very close to 0, means it's very unlikely. Okay, so typically less than alpha. That's usually how small it needs to be. Okay, therefore we will reject the null hypothesis and conclude the alternative hypothesis. Now p-values close to 1 mean no surprise, typically greater than alpha. Okay, typically greater than alpha. Therefore we would fail to reject the null hypothesis. So just keep track here. There's a lot of different p's, right? There's like p, p naught, p hat, and then p value. Okay, they're all different. Okay, p by itself, p just by itself is population proportion. P naught or p0, that's population proportion if the null hypothesis is true. P hat, that's sample proportion. And whenever you see this p value, it's always together. It's always together, right? All that is the likelihood of observing our data given that the null hypothesis is true. Okay, so try to keep track of all these different p's that are floating around here, and I'll be sure to help you out. Okay, so just to bring things home here, so I want to find the p-value for this example, right? And so what I find here is that so because it says here the test statistic value as extreme or more extreme than the value we actually observed. So here we observed this value here, okay, 0.5230. So what we want to do, the p-value is probably observing this, right, or more extreme. So because more extreme means larger, because remember our alternative is larger, right? So that means we're going to reject if our proportion is a lot larger than 50%. So our p-value is that. And actually, what we can write in here, right, because this is equal to, because remember we found the z-score, right? Because we're using a central limit theorem. We're saying sample proportion follows a normal distribution. So this is z, what do we get? 0.77 roughly, okay? Okay, this here was our test statistic value, right? So really when we find that z-score, I mean, we can interpret it, but we're going to use it to find a probability, right? So really it's the probability of observing 0.5230 and larger values. That's what they mean by extreme. And this alternative is always going to tell you which way to go, right? So this p-value here, so assuming, and how we found this number here was assuming the null hypothesis to be true. Right, so that's how we break down this p-value, right? Assuming null hypothesis to be true, extreme or more extreme, right? So this alternative tells us the direction of extreme, and how we calculated this z-score or z-test statistic, we assume the null hypothesis to be true. All right, so we're just saying, so what this represents is that, well, assuming that the true proportion of candidates selected is 50%, the probability of observing our data of 52.3% in more extreme values is 22% chance. So for us, that's pretty likely to observe it, right? So in this case, since our p-value of 22% is larger than alpha, which is 5%, there was no surprise here. Okay, no surprise. And we conclude that there's enough evidence. There's not enough evidence to conclude kids prefer candy treats over toys. Okay, so this value here would need to be like, less than 5% in order for us, right? So it means something very unlikely to occur. But 22%, that's pretty likely, right? Meaning that if the true proportion is 50%, this sample proportion is pretty likely to be observed. Okay, so no surprise here. Okay, all right. But now what we're going to do is get into a more formal method from beginning to end in hypothesis testing again. But we'll come back to that in a bit.